Aha! Okay. Welcome on this Monday. This is an explanation video. It is not a new information video. And I'm going to look today at question 16.37 and try and see if we can get a bit more comfortable with how this worked out. Now, I think two things happen here. First of all, you're told the percent ionized. I think you would have been more comfortable if it gave you the pH. And that, and the other thing that I don't like in this question is that the molarity and the percent ionization are the same value. That weirds me out a little bit now that I take a look at it. So here's how I solved it. The first thing I did was figure out the amount that I ionized here. So I took this 0.30 molarity, and I multiplied that by 0.00030, and this is the percent ionization as a decimal. And I got this value of 9.0 times 10 to the negative 6. And this is going to be two things. It's going to be the B plus, and it's also going to be the hydroxide. So it's going to be how much of each of these things we have. And some of you guys did this and immediately realized, I don't even need a nice chart for this. I got everything I need, but I'm going to do it anyway. Okay, a couple other concepts. Because this thing's falling apart, we get the same amount of both of these things. So because it's 0.03% ionized, you simply take that initial concentration times the percent ionization as a decimal, and you get both things here. All right, so let's set up the ice chart. We're going to have our non-dissociative base. We're going to have our conjugate acid, and then our conjugate base here. So here we go. Initial is 0.030. An initial on these guys is going to be nothing and nothing. The change on this is going to be a negative x, and this is going to be in plus x on both of these. And then at equilibrium, this is going to be equal to 0.030 minus x, and this will be an x, and this will also be an x. And because we know this, this is our x here. This is how much it dissociated. X is equal to this 9.0 times 10 to the negative 6. So our Kb expression here, Kb, which is what we're trying to find, is equal to, on the top, the two ions. On the bottom, the non-dissociated. So Kb is equal to, on the top, this 9.06. No, it's 9.0. Where did I get that second 6 from? I apologize. My bad. Let me just grab an eraser. Okay. And now let's go back to the pen. Times 10 to the negative 6. Concentration times the same thing. And I could show it as squared, but I'm just going to put it in each here. On the bottom, I have the initial concentration minus the amount that was dissociated, minus 9.0 times 10 to the negative 6. You only need to subtract it once because it came apart into these two particles. And that gives us our Kb value of, I got 2.7 times 10 to the negative 9. Small. Like really small. So we get these small values for these things because these are weak particles. They're not producing a lot. Anything that ionizes 0.03% is not going to have a gigantic value. Most of it is sitting on the bottom. And remember what Kb actually is. Kb is on the bottom is the reactant, and on the top is the product. And most of this is reactant. It's only reacting 0.03%. So most of it has to be on the bottom. So it's going to create that great big negative exponent like that. So that's how it works out. That is our solution to this. Most of you got the first two right. Some of you kind of gave up on this one. I'm not sure why. So I gave you a bit more practice here on the Monday, and then I'll take a look at Friday's practice as it comes in over the weekend, and we will evaluate where we are. This is one of the last big skills that I want to do with you guys this year, and I want to make sure we understand it well. All right, I hope this helped, and I hope you're doing well. Take